Hi, welcome to my session for the title of Comparison of Electronically Switchable High Q Bandstop to Bandpass Filter based on All-Pass Network. I'm Mohammad Khairi bin Zahari as a presenter, and the co-authors for this paper include with Dr. Badrul Hisham Ahmad and also Nur Azwan Shairi. So this is the abstract of my paper. Alright, filters are the basic components of the transmitter and receiver in the microwave system, either for band select or band reject units. Meanwhile, switchable microwave filters are highly impaired on the modern technologies, especially for the cognitive radio applications. So in this paper, a comparison of 4 different types of resonators in electronically switchable high Q bandstop to bandpass filters is reported, which are parallel couple, dual mode ring, step impedance dual mode, and also T-shape. So these filters are designed based on lossy resonators, where it can be used to partially compensate for the RF losses. These switchable filters provide 2 modes of operation, which is band stop and band pass response. In this comparison, all the filters are operated at 2.4 GHz frequency. The return loss and insertion loss for the band stop filter is below 15 dB, while for band pass filter, it is depending on the type of the resonators. Now let's move to introduction. So this switchable filter is the most suitable mechanism that has been implemented recently in the microwave system to change response at the bandpass or bandstop. For example, in cognitive radio environment. So this filter is used in the radio system to select signal of interest or attenuate interfering signals. It depends on the environment or mode of operation of the radio. In this paper, the comparison of switchable bandstop to bandpass filter from previous work is discussed and presented. The electronically switchable filter was designed using microstrip technology. So the electronically switchable filter response using lower Q lossy resonators was investigated based on the simulated and measured results. So in this work, pin diodes and varactor diodes were used to control the switching operation between bandstop and bandpass response. So the methodology of this kind of filters is based on the all-pass network fundamental. So the perfectly infinite stop band attenuation of the band stop response can be produced by using 2 lower Q lossy resonators in microstrip technology and has been proven by the author, by Andrew Gayed. The fundamental of this theory was from also in Andrew Gayed papers, which built upon the perfectly notched concept. The design was consisted of 2 identically lossy resonators connected to the 90-degree hybrid coupler or directional coupler. Therefore, its advantages are not only to produce higher stop band attenuation, as well as being perfectly matched in both the band pass and also the band stop. Let's move to the next slide. This is the high Q band stop filter fundamental. All right, this is the equation for S11 and also S12, return loss and the insertion loss of the concept from this filter. So switchable bandstop to bandpass concept. The concept of switchable bandstop to bandpass filter is shown in figure here. So in pin diodes in the circuit are used as a switching element by respecting to the symmetrical design of the filter. So all filters were designed based on the lossy all-pass network and applied to 4 different structures as mentioned earlier, which is a parallel couple, dual mode ring resonator, step impedance dual mode, and also T-shaped resonators. So this is the concept of switchable bandstop filter. This is the first design or the implementation of parallel coupled resonator. So as you can see that this filter have a pin diode here and the biasing line here. This is the biasing line and this is the bias for the pin diode to activate it. This is the response of bandstop filter. As you can see, the operation of the filter is based on the pin diodes, which is acted as a switching element at the on or off. When the pin diodes were supplied with 5 volts, the pin diode switch on and high Q bandstop was produced. Stop filter resonate at center frequency 2.4 GHz, where the insertion loss is 30 dB and the return loss is 18 dB, as you can see. So this filter produce a very high Q bandstop, right? Compared with the measurement result, we can see that the filter is shifted to 2.38 GHz with the insertion loss 20 dB and return loss 10 dB. So for the unloaded Q factor was 71. Let's move to the bandpass response. This is the bandpass response. As you can see, when the pin diode is turned off, right? Let's move to the T-shape resonator. This is the T-shape. It's based on the same fundamental, right? This is the result of bandstop response, and this is the bandpass response. So this is the dual mode ring resonator, right? It's based on the ring dual mode resonator, and we placed a varactor diode at here in the transmission lines to make a tuning so that the filter can produce the bandstop or bandpass response. So this is the bandstop response for the dual mode ring resonators, where we can see that it's a very high Q filter here, right? And this is the bandpass response. This is the step impedance dual mode resonator implemented with the same concept, all right? So this is the pin diode. We can see here. This is the biasing for the pin diode. This is the response of bandpass filter. And this is the bandstop response. Okay, let's move to the comparison of unloaded Q for different resonators. As you can see at the table, right, we have 4 types of resonator: parallel, couple, dual mode ring resonator, step impedance, and also T-shape. As you can see that here, for the unloaded Q factor for bandstop filter, the most high Q is a dual mode ring resonator, which is 160, and the lowest is the step impedance. All right, so we have a difference of bandwidth, 3 dB bandwidth, and we can see that the difference of pin diode or varactor diode used in this filter design. And also in terms of comparison, we compare with the size of the filter. From table 1, it is shown that the performance of 4 different resonators that offered high Q factor for bandstop filter, which can be switched electronically to bandpass response. So based on the comparison, dual mode ring resonator offered a better result with a high Q bandstop, which was 160. Meanwhile, the Q factor for the T-shape and parallel couple resonator was 76 and 71 respectively. The step impedance of the unloaded Q factor was 42, which is lower than the others. So in this comparison, it also shows the number of pin diodes and also varactor diode for the filter. The T-shaped resonator only uses 2 pin diodes, and step impedance resonator uses 3 pin diodes. For dual mode ring resonator, it uses single pin diode and 2 varactor diodes by reducing the number of pin diode and varactor diodes. This can potentially reduce the cost of fabrication and the development of the switchable microfilters. And lastly, from the table also shows that the parallel couple has the larger size compared to others, which is 70.6 times 49.7 mm. So then followed by the dual mode ring resonator, T-shape impedance dual mode resonator. So in conclusion, the comparison of 4 designs of switchable bandstop to bandpass filters are presented. The comparison were made based on the unloaded Q factor and the quantity of pin diode varactor diode used. The following conclusion can be made from the present study, in which the design of the switchable microwave filter was successfully investigated and achieved. So the design concept has been successfully presented with the support of RF and microwave theories, and it was simulated and compared with the experimental results. All the design filters were fabricated onto Rogers Droid 5880 boards. The suitable concept, topology, and mechanism of the bandstop filter with the reconfigurable techniques are discussed. Besides, the use of switchable bandstop to bandpass filter has been proven in the experimental result and can be integrated in the cognitive video. So this is the references for my paper. So that's all from me. Thank you.